All right, this is the first of two videos on nuclear chemistry. So this is part one. And the story of nuclear chemistry starts with Antoine Becquerel. And he worked with the Curies, Marie and Pierre Curie, at the University of Paris at Sorbonne. And the year was 1897 when radioactivity was discovered. Becquerel worked with a material, it was a mineral salt that was mined in the Alps in Austria. And he was doing experiments on it because it had this kind of natural radiation associated with it, a glow. And this material called pitchblende was shipped from Austria to Paris, and they studied it. It started with just Becquerel, so Becquerel studied it. And, for example, maybe this is a rock, a sample of pitchblende material, contains uranium, and the radiation was not understood. His theory was that it was a sunlight-induced process. Sunlight-induced radiation. And so here's the sun over here. The sun is shining light down on the uranium contained within this rock, this pitchblende material, and it would cause a secondary process of emission to occur. That was the theory. So it turned out that it was bad weather during a certain week when he was studying this material in Paris, and so he couldn't study the effect of sunlight on it, so he covered this rock with black cloth, put it in the drawer on top of the photographic plate, which he was using to record the radiation, took off for a week, came back and expected not to have any radiation having been emitted during the week because of the lack of sunlight. But when he opened it up and unwrapped the cloth and looked at the photographic plate, he saw that emission had occurred and that there was evidence on the photographic plate. Certain parts of the plate had developed spots. So his theory about sunlight was incorrect, and instead he decided that it was a spontaneous emission of radiation, not induced. Okay, had nothing to do with sunlight. All right, and then he called this radiation radioactivity, continued to study it. So here's the sample again, spontaneously emitting radiation. The next step was to put a barrier in front of it with a hole in it, piece of a metal plate or a wooden piece of wood or something, which then causes a collimated beam of radiation to come through. And then you get the photographic plate over here to record the radiation. It had an effect on the plate. And then, the C magnet. So you take a magnet like that. That's just one example, but one that we're all familiar with. So a C magnet has a north and south pole. And what he found in the presence of the magnet is that the beam broke up into three parts. One was attracted to the north pole of the magnet. One was unaffected by the poles of the magnet. And then another path was associated with being attracted to the south pole. All right, so this meant that at least two of these, or it meant that two of the particles were charged, and the one that goes to the North Pole is negative. Negative charge is attracted to the North Pole, And then this one would be the positive charge attracted to the South Pole. And then this one was neutral. And he gave them names, alpha, beta, and gamma. So alpha is the symbol for the positively charged particles. There are a stream of particles that were hitting these plates. The negatively charged one is called beta, and the neutral is gamma. So alpha, beta, gamma. Okay, so beta turned out to be a high energy electron, which means it's moving fast. Gamma is neutral, and this one is electromagnetic radiation, high energy photons. And then the positive charge turned out to be a helium nucleus. So helium-4, for example, has 2 protons, 2 electrons, and 2 neutrons by difference of 4 minus 2. But if it's a helium-2 plus, then it's missing the 2 electrons. So this helium nucleus is 2 protons and 2 neutrons with a positive charge. The high energy electron has the symbol E minus 10 or beta minus 10, or sometimes you just see beta. And the negative 1 in this lower left position is usually where you put the number of protons, the number of positive charges, but in nuclear chemistry we kind of expand that definition. We just say that this is the charge, and in this case it's going to be negative if it's an electron. All right, then the symbol for gamma is 0, 0. It doesn't have any protons, it doesn't have any neutrons. And then the one for helium, as I said, 2, 4. Now this 2 plus charge here is present, but it's never really included in the notation. It is charged, but the focus is not on that. So then that's the alpha particle. Okay, so those are the symbols for those. The story continues with Marie Curie, right? So Pierre Curie was a professor at the University of Paris with Becquerel, and Marie was married to him and living in Paris. She was originally from Poland. She had the equivalent of probably her master's degree from University of Poland, and she wanted to work on her PhD in physics, and she wanted to work with Becquerel. It turned out back in 1897 that women were not allowed to do research in the laboratories. They weren't allowed in the building, and so to set up a lab. And so because they knew her to be a brilliant scientist, they agreed to take her on and put her in the woodshed on the campus of the university, and they built a little lab in there for her. So and there's photos of her online that you can find where she's slaving over, vats of boiling liquids, and she's in the middle of these experiments. And her job was to take this pitch blend, and it was coming by the ton from Austria at this point, and her job was to chemically extract the uranium out of the mineral salt material. So she was able to do that through these solvent extractions and different things. And it turned out that not only did she extract the uranium so that it could be studied alone, she ended up extracting 2 other elements, polonium-84 and radium-88, and they were brand new. So they turned out both to be more radioactive than uranium, so it accounted for a lot of the emission. And she got the Nobel Prize for that in chemistry for discovering 2 new elements. So that is a great story. Marie Curie is a role model for women, and what a story for the gal who was working in the woodshed. course, it helped to have her husband as a professor, right? Anyway, okay, so let's see. Here's more on the symbolism of these different particles. Alpha or helium 2+. Again, sometimes you see that 2+, sometimes you don't. Beta, electron negative, or beta -1. Gamma 0 to indicate it's neutral. But there are other particles as well that are given off by other substances. The proton, rarely you see this beta with a positive. So, yeah, I would say probably you don't see that too much. This one though, the proton has 1 proton, and then the sum of 1 proton and 0 neutrons gives it a 1 up there. Neutrons have no charge, but they have 1 neutron, obviously. They are the neutron, or it is the neutron. Positrons are like electrons. So electrons have negative charge and certain mass and so on. It turns out that the positron is exactly like the electron, same mass, same thing, except that it's got a positive charge instead of a negative charge. So see the difference here and here. Yeah, this one just don't even think about. And then you got beta as the beta positive as opposed to beta negative, excuse me, for the positron. All right, now here is an example, and I think this one has a typo. Yes, it does. I will correct that. So this is 238, U-238. That's a very well-known isotope of uranium. And here's an example of a nuclear reaction where you see that the charge is conserved, that 92 positive charges on the left ends up, you have 1 particle breaking up into 2, and you have uranium forming a new element, thorium. So it's a nuclear reaction, and in this case, the helium alpha particle is given off in the process. So for the nuclear reaction, you have 1 element becoming another element, and then some other particle is involved in it. All right, so then remember the number of neutrons is the difference between these two. So in this case, it's 6 and 4, 1, 4. All right, and then you take the difference for thorium. This is going to be 4 and 144, and then this one is going to be, the difference is 2. So you see that the number of protons, the number of positive charges are conserved, but also the number of neutrons are conserved as well. So that's one of the properties of these nuclear reactions. Okay, here is a very interesting diagram of what happens to uranium-238. So the very first one that I talked about on the last slide is right here. So uranium becomes thorium and an alpha particle is emitted. Then thorium becomes protactinium, and this time you have a beta particle. So if you look at what's going on with the beta here, remember beta is the electron. So you would write here thorium forms protactinium plus an electron, right? And then notice that you get the conservation again. So you've got 90 is equal to 91 minus 1, and then 234, 234. And in this case, the only thing that's happened is that the electron has been emitted. No, I take that back. So it's going from 90 to 91. So a proton has been gained. And in order for this to be constant, the neutron has to be lost. I'll talk about that more in a bit. But in any event, all these nuclear processes are taking place. Uranium is radioactive to start with. And it just keeps on going. It keeps on decaying. Some of these pathways are millions of years for their half-lives, which means half of the concentration after like a million years, something like that. And then some of them are very short, milliseconds, microseconds, nanoseconds. So then you have thorium, radium, radon, polonium. This is the one Marie Curie studied. Lead, bismuth, polonium, and so on, until finally you get down here to lead-206, and it turns out that that's stable. It's not radioactive. So there are some elements that are radioactive and some are not. Lead is one example of an element that is not radioactive. So why is there so much lead on Earth? Because these radioactive elements decay over millions of years and until they form something stable. Okay, that's one way you can interpret that. All right, now here are some of the examples that were on there. These are examples for alpha decay. You can study them in detail. You see 86 plus 2 is 88 and so on. And then here is beta decay, and beta is the electron, right? So negative for the electron. And okay, now we can talk about this in detail. So carbon is giving up a beta, but in doing so, it's gaining one proton. Okay, so this reaction is taking place inside the nucleus. So if 14 and 14, if those numbers are the same, that means the sum of the protons and neutrons are the same. If it's gained a proton in this process, then it's lost a neutron for the sum to still be 14. So you see here that the fundamental process is the neutron turns into a proton, and when it does that, the electron is given off. And here's another example of europium and gadolinium doing the exact same thing. All right, then you have positron emission, and this one is has some similarities. You have technetium here, and it becomes molybdenum, so 43 to 42, and you got 1 left over. So this has got to be a positron. Remember, it's an electron with a positive charge. So what's going on here? It's losing a proton, but 95 and 95, that stays the same. So if it loses a proton, it's going to make a neutron, which is exactly what this says. The proton becomes a neutron plus a positron. Okay, so that can happen. Then we have electron capture as another process. This one's interesting too. So you have potassium, and there's a typo here as well. Let's fix that. 19. A couple typos in here. Okay, so you have potassium 19. Okay, in this case, it's very interesting. The nucleus in potassium steals an electron, one of its own electrons in the core. So you know there's all these core electrons, and then you have the valence electrons on the outside. One of the core electrons that's very close to the nucleus gets grabbed by the nucleus. And so it disappears, and then let's see, you have 19 minus 1 is 18 happening here. And then since this is just an electron, the number of neutrons, well, let me take that back. So you got, these are now the protons decrease, so then you got an increase in a neutron, right? So proton plus the inner core electron forms a neutron for electron capture. Then you have gamma radiation. This is the gamma symbol right here. So in this is actually one that's very useful for medical research. So you see this little M right here. That means metastable. And metastable means that, you know, it's been created in a highly excited state, which is not that stable, and over time it's going to decay to a stable state. So metastable goes to a stable state. And how does it become metastable? It could be that it's exposed to some high energy radiation, and just some of that energy gets absorbed by the system. So in time, it'll go 99M to 99, and the only thing that's happened here is that light's given off. So, and then that light is very useful in medicine. I'll show you some examples for that. Okay, getting there. So here we can see the effects of different radiations. All right, and so you see if you have alpha, beta, and gamma particles moving in from left to right. If you put a tissue, like a Kleenex tissue, in front of it, that's enough to stop the alpha particle right there. It's not going to go any further. The beta particle can actually go straight through. This is a high energy electron. It can go straight through, but then if you put a piece of aluminum in place, it'll stop it. The gamma particles, on the other hand, can go through tissue, can go through aluminum, can go through concrete, and then if we have lead, lead will stop it. So maybe you've seen on TV or in documentaries people working with nuclear materials. Usually it's encased, the whole experiment is encased in lead so that there's protection from the gamma rays. So think about it, if you were exposed to a nuclear explosion, maybe a nuclear power plant that went wild and melted down, blew up, you got all these particles and more coming at you, and what will the story be? Well, it turns out alpha can do the most damage, so it's a good thing that it would get stopped by our own skin. Okay, so alpha particles are not going to go through, but they could do damage to the skin. Beta particles can go through our skin to our organs, and gamma, forget about it, also can go through our tissue, our skin and our tissue. Okay, come back to that. So here is information if you happen to be like a radiation technician, you might be interested in how much radiation you can tolerate before getting leukemia. So the idea here is that the cells that divide fastest are in the bone marrow, and they're the ones that are most affected by radiation. You can get mutations that way. The DNA can be damaged. So leukemia is the disease associated with cancer of the bone marrow. And you know about it because it's got a white blood cell count decrease. So when the Chernobyl nuclear power plant meltdown happened, the people in the town and further out, but the ones certainly close to it, had severe problems associated with their bone marrow. There were doctors from UCLA who went there to Russia, at the time I guess it was Soviet Union, and did bone marrow transplants. It was amazing. I remember that. And saved lives. Not everybody made it, but a lot of damage that actually got into the plants and animals, and it's a tough situation. Anyway, how much radiation can you handle? That's the issue here. And so you want to have a measurement of that, and these are called REMS. Personally, I don't think this is a very intelligent name. But I do know that Röntgen was a scientist who's, I think, I'm going to say he discovered the X-ray, but don't quote me on that. So anyway, he was associated with studying radiation doses and so on. And so it's just a product of these two terms. You get the absorbed dose in 100 joules of energy per kilogram of tissue, and then you got to multiply it times the RBE. Now, by the time we got to Fukushima, the power plant that melted down in Japan, I don't know when that was, within the last 10 years probably, instead of talking about, what was it called? Instead of rads, it was sieverts. So when you read about Fukushima, you'll read about how many sieverts there were, and I think the difference might be 1,000 joules instead of 100. Excuse me, but anyway, you can go back and forth. So, but we're focusing here on 100 joules of energy per kilogram of tissue times the RBE, and the RBE is given here. So, excuse me. All right, relative effectiveness relative to 1. So the X-ray, the gamma ray, the beta ray, and some slow-moving positrons pretty much have the same type of effect. Positrons moving fast can have about 5 times that amount. Protons about 5 times more than the beta or the X-ray or the gamma ray. Neutrons can do quite a bit more damage. They've got way more energy, 5 to 20, and there's alpha I mentioned before. It's a good thing it's stopped by your skin because it could really do a lot of damage. Um, Now, these different types of radiation can be useful for medicine. X-rays are used to image bones. Gamma rays, there's two different kinds of counters. There is the Geiger counter and the scintillation counter. The scintillation counter is what is used in medicine. And it's looking at the fact that gamma rays might be in your body, used as a tool maybe to destroy a tumor, and then it can actually destroy the tumor, but at the same time it can come out through the skin and you can detect it using scintillation counting. Beta also can go, those electrons can go through the skin, used to kill tumors. I had a neighbor some years ago, a young high school student who had he had thyroid cancer, and it was a very, very bad case of it, and he had to go into quarantine in his home. He had to take radioactive iodide, so I minus, that was radioactive, so one of the radioactive isotopes of iodide. And then the half-life for it was about a week. I think it was 8 point something days it would take for the concentration of it to actually decompose the half of that value. So he was in his room for a couple of weeks actually until the radiation subsided. And the radiation, so you take a pill just like you take, maybe you take some vitamin kind of thing. Excuse me, but this had iodide in it, and so the iodide tends to concentrate at the thyroid. And that is what happened. So the iodide is radioactive. It destroyed the tumor in the thyroid, but at the same time, the iodide's also coming out to the scintillation counter, and it was possible to image the thyroid as it, the tumor, I should say, as it was shrinking. And in the case of my neighbor Ryan, he actually made it. He was going to UCLA for the cancer doctors. They were some of the best. But his case was bad. It was from hereditary from both sides of his family, so they really didn't give him a lot of hope. But he had numerous treatments, and there's really only so many you can have. In other words, there's a maximum amount you can have before you can't have any more. And he went through all the way to the max with it, and then he was cured. So that is a great story. All right, anyway, so positron here. Positron, this is interesting, plus an electron forms two gammas, and the gammas are detected with the scintillation counting. So the PET scan is a positron emission tomography scan, and it's monitoring what's going on with the positrons. So you can have a source for positrons somehow getting into your cells, and they're going to interact with the electrons there, and it can be useful for imaging. Proton therapy, also similar, using imaging techniques. And then neutron, no. Alpha, no. All right, that's interesting for medicine. And here are some of the isotopes used in medicine. I was just talking about iodine 131. 8.1 days is the half-life for thyroid. And then you just look all over the place. You got red blood cells, metabolism, tumors, eyes, red blood cells, bones. All these different radioactive isotopes can be used. So that is the story with the scintillation counter and how you can image tumors and different organs and so on. Very exciting. All right, so this topic has to do with determining whether a element or an isotope is radioactive or stable. And we're going to be looking at 4 criteria here. I'm going to make a list of them. And the first one is on this slide. We're going to look at the atomic number of the element or the isotope. Probably should be using the word isotope here. Second, magic numbers. Third one is pairs of proton and neutrons. And 4 will be the valley of stability. So we have to consider all 4 of those, and some of them will get a little bit higher priority in our determination, but in general you really have to look at everything, and if you do that, most of the time it becomes clear whether something's radioactive or not. All right, so we'll start with this first concept here. We want to look at the atomic number. So here's the rule that all isotopes with atomic number greater than 83 are radioactive. So 80, I'm looking at the periodic table here. 83 is bismuth. So bismuth, 83, and then the next one is polonium, 84 in the table. So right there, everything greater than 83, that's a nasty looking B there, would be radioactive. And it's easy to remember because polonium is the element that Marie Curie discovered, right? Okay, so there's that. And then when you get further into the periodic table down to, so in other words, from 84 to 92, which is uranium, these are radioactive elements that are found in nature. And every isotope of these elements are radioactive. Now, going past uranium, starting with neptunium, 93. After that, all the way up to 118, these elements are all radioactive as well, but the difference is that they've only been seen in the laboratory. They've been synthesized using high energy collision techniques, the cyclotron, the linear accelerator, and nowadays we have that huge accelerator machine in Switzerland. You probably heard about CERN, C-E-R-N, and it's possible to collide elements with particles at very, very high energies, and nuclear reactions take place. And new elements are discovered, among many other things. So anyway, that's the atomic number. If you got, some element 91, then it's radioactive. Every single isotope is radioactive. Same with all the elements after, starting with polonium. All right, 2 and 3 are on this slide. And number 2 here is the shell model of the nucleus. So you have this concept from studying the electrons, that there's stability associated with the electrons when they pair, and that's an angular momentum issue. There's just stability, those magnetic moments kind of line up, and all kinds of interesting things. Same thing happens with protons and neutrons, but it's not as easily defined as it is with the electrons. We do know that they exist in levels, energy levels, just like the electron does. There are filled shells and subshells that are associated with stability, and the magic numbers are a reflection of the stability. So there is stability associated with 2 protons, 8 protons, 20 protons, all the way up to 82. And then neutrons, similarly, you have 2, 8, 20, 28, 50, 82, but one more, 126. And if you look at the example here of lead, we've already talked about lead and the fact that it's stable. So what happens if you subtract, so 82 is the number of protons. If you subtract, you get 126 neutrons, right? And so look at the magic numbers here. The number of protons is 82, the number of neutrons is 126, so you can bet that this isotope is going to be stable, not radioactive. Okay, then number 3 on the list of determining stability, I guess, or radioactivity. So here, this is an interesting table. If you look in your book, the numbers might be a little bit different, but that part doesn't matter. But here's how you interpret this table. So there are 157 stable isotopes that have an even number of protons and an even number of neutrons. There are 52 stable isotopes with an even number of protons and an odd number of neutrons. There are 50 stable isotopes that have an odd number of neutrons and an even number of neutrons, and there are only 5 stable isotopes that are odd-odd. So chances are, if you're looking at an isotope that has an odd number of protons and odd number of neutrons, chances are it's not one of those 5, meaning that chances are it's going to be radioactive. So that would be a pretty strong criteria, but not absolute. Okay. All right. So then, last slide. This is the one that takes a little time to talk about. And this is the plot of the stable nuclides found in nature, also called the Valley of Stability. So first of all, what is this thing? What is this beast? You're plotting here neutrons versus protons for an element or for an isotope. Okay. Then you have you can see that sorry. Back up there. All right, so you can see this solid line here. This is the line of slope equals 1. So this is 40 protons and 40 neutrons, 70 protons, 70 neutrons. It's just a line, it's on the graph. Okay, and then what you see in the dots are the isotopes with certain numbers of protons and neutrons, and that these isotopes are stable. So the little dots here are for many, not all, of these stable isotopes. And you can see that, for example, down here, and there's a typo on one of these. Which one was it? Yeah, it's this one. Okay. So this should be a 1. That should be 1. Excuse me. All right, so with elements or isotopes, I should say, that have low numbers of protons. So in this region, we see stability is associated with having equal numbers of neutrons and protons. Then, as the atomic number increases, we find that stability is associated with having greater number of neutrons than protons. So this one has 30 protons and maybe 35 neutrons. Well, here's an example with silver going up in atomic number. With the silver, this is 47 here for the protons, but then this is going to be 60. Well, I don't think their line here is exactly right. It should be up here. But anyway, so if you look at the ratio of the neutrons and protons, so down here in the case of iron, you have 26 protons, that would be here, and 30 neutrons. That ratio is 1.15. In the case of silver, you have 47 protons, and by difference, you've got 60 neutrons. The ratio, the N over P ratio, is 1.28. So you can see it starts out N over P being 1, then 1.15, 1.28, and by the time you get all the way up here to tungsten, it's 1.5, right? 1.49. So the N over P ratio increases for those isotopes that are stable, and that's as a function of the number of protons. So that's the key to this. And let me just look ahead one. Okay, I think my slides got messed up here. The order. Okay, sorry. Anyway, okay. Now what we want to do is just look at a few examples here for the Valley of Stability so we can see what's going on. And what we'll find is that the elements, that are outside of the Valley of Stability, those isotopes are radioactive. And so the radioactive process is one in which, beta electrons are given up, or alpha particles, or gamma, whatever, is a process which brings it closer to the Valley of Stability. So the emission takes place, and then the new isotope is created, and the new isotope will be closer to the Valley of Stability than the one it started with there. So the type of radioactive emission to the left-hand side of the Valley of Stability would be alpha or beta. So decay by alpha or beta emission. And then to the right, you have positron emission. And also the possibility of electron capture. So I don't want to go over too many of these, but I wanted to show an example here. All right, let's look at a few details here. This is for electron capture. And the example is a proton plus an electron gets converted to a neutron. Potassium 1940 is an example where it picks up an electron from its inner core and converts to form argon 1840. And we can calculate our neutrons, 21 and 22. If you look at the N over P ratio here, 21 over 19, 1.11. And then 22 divided by 18, 1.22. So we see that electron capture then increases the N over P ratio. And if we just kind of did a blow up of the valley of stability graph, N over P, 21, 22 neutrons, and 18, 19 protons. The potassium is 1921. The argon is 18 and 22. And so the transformation to argon involves a shift up and over to the left. And if you try to find that on the valley of stability, argon you would see would be closer to or actually on the valley of stability than potassium. So that would be the motivation for the process. If you look at positron emission, this is the one where you have the proton becoming a neutron plus an electron. Example here is technetium 4395 forming molybdenum 4295 plus a positron. It's got a positive there, positive one instead of negative one. And then N over P is 52 over 43, 1.21. N over P for molybdenum, 53 over 42, 1.26. If you look at the difference between them, you see that N over P ratio increases for positron emission. And this one, let's use 42 and 43, 52 and 53. So it starts out with 5243 right here. This is technetium. And then it goes to molybdenum, which is 4253. So this is a move up and then over to the left. And if you check it out, this isotope should be, either on the valley of stability or closer to it. So these two examples show you that electron capture and positron emission both happen to the right of the valley of stability. That was kind of a general statement that I made earlier. And then let's go ahead and look at to the left of the valley of stability. The next one is beta emission. And this process is a neutron forming a proton plus an electron. Example here is europium 63-157 forming gadolinium 64-157 plus an electron, N over P ratio is 90, calculate 94 for the neutrons, excuse me, and 93 for the neutrons here. Let's move this down a little bit right there. So the N over P ratio is going to be 94 over 63, which is 1.49. For europium, for gadolinium, it's N over P is 93 divided by 64, which is 1.45. So here you see that the N over P ratio decreases for beta decay. Now, if you looked at those numbers on a graph, let's see, we have 63 and 64, 93 and 94, and the europium is 63.94, gadolinium is 64.93. So this one goes down and then over to the right. So the top one was europium, bottom one was gadolinium 64. Okay, so then that is to the left of the valley of stability. So you'd see this transition towards this valley of stability associated with beta decay. Now alpha decay, the last one, is different. And here it is, remember, a helium 2-4 being formed. So this is a loss of 2 protons and 2 neutrons. And anyone you look at, it gets complicated. But if, for example, you looked at uranium 92-238 forming, let's see, thorium 90-234 plus helium 2-4. Then you have the difference here 146, the difference 144, N over P is 146 divided by 92, 1.59. Then if you look at 144 over 90, that is 1.60. That is a very small change compared to the other changes that we've seen. And you just say there's a slight increase, but that's not the entire story here. So what is it that actually is going on with uranium-238, which is a very important isotope, by the way, for nuclear reactions, nuclear power plants, explosions, bombs, everything in between. So I'm not going to give you the details here, but you got uranium-92, and I already showed you this information in a little bit different format. But that's going to decay to form thorium, and let's just skip all the atomic numbers and stuff. So this is alpha decay. Then it goes to protactinium here by beta decay up to uranium-92, 234, and then it keeps going. Thorium, radium, radon, and so on. There's alpha, 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 and then beta, and so on. And then finally it gets down to lead 82, 208. And the difference there I mentioned before is the 126. So if you look at this one, I mean, if you just look at the big change here, 92 over 238, difference is 146, forming lead 82, 208. The difference here is 126. Remember, 82 and 126 were those magic numbers. And so that is a motivation as well, that pairing of the protons and the neutrons. But here you have 146 over 92, and that is equal to 1.59, and then 126 over 82, 1.54. So here you got the N over P decreases for this process. This is going on to the left of the valley of stability. And I forgot my B there for lead. So then this last graph, you'd have to play around with a little bit. So we can take 82, 92, bigger differences here. 126 versus 146, neutrons and protons, of course. So uranium is 92, 146. And then you have 82, 126 being lead. And so in this case, it's going over and down. Solid arrow there. And then the valley of stability is kind of like that in this region. So if you look at the big overall process, you get a different result than for beta decay here. So you have it's going down and to the right. Over on the other one, it's going down and to the left. So a little bit different, but in any event, alpha decay is very important, and you could see also the motivation, not only just to give off an alpha, but you got radioactive uranium, and it's becoming very stable lead. And remember, the magic numbers are part of that motivation as well. All right, one more slide, and for some reason these slides got mixed up, so let me toggle through. Solid. Second. This one we've already looked at, but it's the next slide. And here, this somehow got out of the wrong place. But this one now, this is the last slide. And, what if we had two isotopes? Can we predict which one is stable and which one is radioactive? So if we look at, in other words, you got a pair, you have a pair, and you want to decide which one in the pair is radioactive and which one is stable. Okay, so for this first one, we have polonium, which is Z, the atomic number is greater than 83, therefore it's radioactive. And then bismuth is going to be stable. So that one's simple. You don't have to do anything else for that. Oh, well, actually one more point here, that difference is 126, so that's a magic number associated with stability. All right, so you see two things here that would lead to the same conclusion. All right, the next set is potassium 1940 and 1939. Let us take the difference. 39 minus 19 is 20. Here you see odd, not that one, odd number of protons and even number of neutrons. So you want to look at that. And then with the potassium, you have here 21, right? This one's 20. And so you have odd protons and odd neutrons. So that, you don't have to do anything else. You just conclude there that because you have odd, chances are that it's radioactive. Odd even lends much more to a stable, not all of odd evens are stable, but more of them tend to be. So that one's okay. And then the last set here, you have gallium, and I think there was a typo. Let me see. Yeah, there's a typo on this one. This is 76. All right, so you can get your neutrons here 40. This is going to be 45. So you have the N over P ratio. You know, you look for, okay, in this case you have odd, even, and then you have odd, odd. So this one most probably is radioactive. Okay, you could stop there, but on the other hand, if you keep going with your analysis here, so if you look at your N over P ratio here, 40 over 31, 1.3, excuse me, and this one, N over P, is 45 over 31, which is 1.5. So there's an increase in the N over P ratio. And you have to go back and look at the band of stability. Remember, you got protons and neutrons. Okay, so let me change color here. So they're both gallium. So pick a spot on the graph, 31 protons for both. One of them has 40 neutrons, which happens to land right in the valley of stability. So that would be 40. And then the other isotope is 45, so it's up here. So that's outside of the band of stability. You'd have to look at the graph to see that at 31, it actually lands right about 40 for stability. So this is going to be stable, which is this one. And this would be radioactive. And that would be consistent with it being odd, odd as well. So, but anyway, with regard to the N over P ratio, okay, this thing is not a slope of 1, it's increasing, right? And so it depends on the number of protons, you know, which number of neutrons fall in that band of stability, and would predict stability based on that. All right, so you get your four criteria. There's the atomic number. You know, if it's greater than 82, then they're going to be radioactive. You get your magic numbers. You want to look for those. Stability associated there. Pairs of protons and neutrons. So you look for even, odd, 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 and so on. And then you want to look in the valley of stability. That's a tough one to look at. Obviously, there's a lot of detail, but you can sometimes come to conclusions with that. All right, that's the end of this section. We got another, we have another video for nuclear chem. That one should be a little bit shorter. And I'll post these right away.